Yeah. And I'm talking to you. Here's my wand. Welcome everybody. This is Cosmic Conversations. This is a monthly talk series that we hold during the semester. Every month we have a talk that's at least vaguely astronomical, although it isn't necessarily science. So in the past we've had talks on astronomy and Hinduism, Islam and the moon, the classical Greek myths and constellations and so on. But tonight we're definitely going to be talking about science. Before I get stuck into talking about where all the elements came from, I want to just highlight a couple of things that we have coming up later in the semester. So next month we will have a graduate student from geology who's in the room talking about volcanoes on other planets. That would be really cool. And then the month after that, in November, we will have a talk that's designed to be kid-friendly, where there will be an opportunity to have hands-on playing around with making impact craters. And that's to coincide with the fact that there will be a comet that we can see with our telescope coming by, and it should become visible towards the end of October, so it'll be visible when we have that talk on, beginning the first week in November. We have a website that you can find. If you Google Cosmic Conversations, you will find it. So you can find out what we're up to, and we're publicized in various other places. Okay, so tonight what I'm going to talk about is where elements come from. But I want to start with a little bit of motivation. So we start with the universe. The universe started with a Big Bang, and it started 14 billion years ago. Now, most of you are going to assume that you believe me, but I want to show you some evidence, some of the reasons why we believe that that is how the universe started. And so I want to bring up Hubble. How many of you have heard of Edwin Hubble? Most of you. He for whom the Hubble Space Telescope is named, and was in fact from Missouri. What he did was, he was measuring the distances to galaxies that are a long way from our own, and also how fast they were moving away from us. Okay? And all he did was to work out how fast they're moving away from us, how far away they are, and plot them on a graph. And so I have a graph here. The horizontal axis is just distance away from us. Parsecs are about 3 light years. So this is millions and millions of light years. Okay? In fact, billions of light years in some cases. And then how fast it's moving away from us. And that's in kilometers per second, so it's moving very fast. And you can see that the 5 galaxies that you looked at, they came out to have this really straight line distribution in this graph. And that was somewhat curious. So we went back and said, no, I need to measure some more. And lo and behold, measuring more didn't change anything. You still got this straight line trend. Well, how can you explain this? How can you explain that you've got all these galaxies, and the ones closer to us are moving away from us, but the ones further away are moving away faster? Okay? And so I'm going to show you how this works. So Hubble came up with this idea that has to do with how these things move. This is going to reset in a second. So if we think about where things are in space, come back, reset. Not going to reset. Okay. Come back. I'm so good with technology. There we go. All right. So here we have. This is just space, and all I've done is that I got the space, and I got these 5 galaxies, and I put them on this space, and they're equally spaced. That's not real, but it helps show the point. And so they're 100 megaparsecs apart, okay? And so what does that mean? They're about 300 million light years apart. Now, what happens if space gets bigger? Well, let's have a look. Space is going to get bigger, and we're going to see these things move apart. Eventually. There we go. And as they move apart, you see that from A, E seems to have moved about 50 megaparsecs. It was 100, now it's 150 megaparsecs. So is B. But C is now 300 megaparsecs away, right? So it's moved further. And D has moved even further, and that's because all of the spaces are getting bigger. Now, what's it going to look like if we're stood on one of the other galaxies? We're going to see that we see exactly the same effect. It doesn't matter which galaxy we're in. We're going to see these things moving away from each other. So now we're standing on B, and we can see that Galaxy A is moving away from us, Galaxy C, Galaxy D, and how far they move depends on how far away from us they are. So you can explain why you get this very simple relationship between how far away something is and how fast it appears to be moving by having space getting bigger. If you want to have another conceptual way of looking at this, if you had a balloon and you stuck pennies on it or something like that, and then you blow up that balloon, the pennies will get further apart, right? It's not that they are actually moving away from each other. The space that they're in gets bigger, okay? And so this is what Hubble came up with, that there must be my technology is just failing me now. There we go. Okay. And so basically the idea, so Hubble's law is that there is this simple relationship between how fast galaxies are moving away from us and how far away they are, and that comes simply from having an expanding universe. What's this got to do with the Big Bang? Well, that was just another demonstration. I won't talk about that. Well, if the universe has been expanding for billions and billions of years, that means that in the past, everything was close together, right? If you just extrapolate that backwards, matter must have been close together because it's all moving apart right now. And if you keep going backwards, if you keep saying, okay, so a million years ago it was like this, a billion years ago it was like this, if you keep moving that backwards, then eventually everything's back at the same point, right? And so that's the Big Bang. So this is the original data on which the idea of the Big Bang is based. That everything started off at a point, and that's how we can explain what we see in the universe right now. Okay. So I don't expect you to read everything on this graph, but this is kind of a schematic of the expansion of the universe. So you start off with everything's in this tiny little space. And to start with, you've got all matter and all energy. And it's just energy to start with, and then matter starts to appear out of that energy. And eventually you've got the components of the matter we're made of, which is protons and neutrons and electrons. And then they combine. And what we're going to get into is how do they combine to make us? Okay? So, back to the question at hand. We started with a Big Bang. Now the universe is expanding. You've made some protons and some neutrons and some electrons. And you've made even some helium. So if we look at these periodic tables that we have on the inside of the room, helium is the first element, it's number one. Sorry, hydrogen is the first one, helium is the second one. And after that, we don't make anything else in the Big Bang. After that, the universe is spread out so much that that's it, we're done. What are we made of?
Carbon.
Mostly carbon. And at this point, most of the universe is hydrogen, and everything else is not made yet. We are actually, by mass, mostly oxygen, partly because it's a more massive element. So we are made of oxygen, carbon, and nitrogen. We actually contain a little bit of just about everything. But none of that existed at the beginning of the universe. So we have to make it somewhere. Where are we going to make it?
Stars.
Yeah. We have to make it inside the stars. So, before we get to that, I just want to talk about what elements are, because this is really important to understanding how we make these things. So I've got these tables up here that show all the elements. Actually, it doesn't because they're out of date, but all of them we care about. And when you have an element, it's made of protons, neutrons, and electrons. In the middle, there's protons and neutrons. If it's hydrogen, it's just a proton. Otherwise, there's protons and neutrons. And then there are electrons on the outside. From the point of view of what is an element, what really matters is how many protons does it have. Okay? And this is really important. If it's neutral, like the atoms in us and in this room are mostly neutral, except for the ones inside the tube. And so the number of protons and the number of electrons match so that they're electrically neutral. The neutrons are just neutral. They don't add anything but mass. They add space, but that's a whole other issue. But the number of protons is what tells you what element you've got. So 1 proton is hydrogen, 2 protons is helium, 3 is lithium, 6 would be carbon, 7 is nitrogen, 8 is oxygen, and so on. And naturally occurring and still existing on Earth, then we have up to number 92. Okay? And we need to make all those. The Big Bang only made 1 and 2, and we have to make the other 91. Okay? So how are these elements made? Well, I'm going to show you this animation. This is how we do the first step, and this is actually what happens inside stars, but also in the Big Bang. So here I've got 2 protons, which is just a hydrogen. Forget electrons. When you do nuclear physics, you don't worry about electrons. And mostly. So what happens when they come together? Well, it's unstable, and actually what will happen is it will do a radioactive decay, and you get this antimatter electron. It's a positron coming off, and so one of them converts itself to a neutron. Okay? Now what happens next is that meets an electron and annihilates itself, but that's energy. So that's all releasing energy. Okay? Then you have another hydrogen comes along and joins, and now you've got 2 protons. So that's a helium. Okay? And then actually another one of those is going to come along and join with that, and you will get helium, and then two extra hydrogens have gone off. I'm just going to show you, this is a static thing, because for some people that's easier to digest. Basically this is the same thing you just saw, where you've got 4 hydrogens on this side, 2 combine and make another hydrogen, but it's got a neutron attached to it, and then you get another hydrogen and you get a helium, and then you get 2 of those, and finally you get this helium that's got 2 neutrons. Okay? In the process of this, it releases energy. Now this is important because this is what happens in the very early universe. You make protons and neutrons, and then you do this to make helium. But you don't get any further than that. You don't make anything bigger than that. When we stick heliums together, it's fusion. This is nuclear fusion. We're sticking things together. We stick hydrogens together. We stick heliums together. We stick all sorts of things together. And when we do that, it releases energy. And the energy is released according to probably the most famous equation ever, which is E equals mc squared. And it basically says that the amount of material that is lost when you do this, and it turns into energy, and that's what fuels the cell. Okay? And it comes from the idea that when you have these nuclei, you have these protons and you stick them together, the thing that you make has less mass. And all the mass that was lost is now out there as energy. But you can also think of it as being what binds it together. Because if you want to break it apart again, you have to give it that much energy to make it fall apart. Okay? So it's called the binding energy. And just to give you an idea of how much of this has to happen, this is what the sun is doing right now. This is how it produces energy to shine. And it is converting 600 billion kilograms of hydrogen into helium every second. Thankfully, it has a lot more than that, so it can do it for a while. Okay, so this is a little bit complicated, but we're going to get through this. When you do this, you basically, what this graph is showing you is how much energy is binding it. So how much energy would you have to put back in to make it fall apart back into its pieces? Okay? So to go from hydrogen at the top to helium, you actually have to give it loses a lot of energy. You would have to give it a lot of energy back to make it fall apart. And you can see that basically that keeps happening. If you then want to stick heliums together, maybe make a carbon, that would give up some more energy. If you then want to make some oxygen, that would give off some more energy, all the way up to iron. And so as you're sticking these things together, you can start to make heavier and heavier elements. You don't just make helium, you can make everything, up to iron. Let's go back to our tables. Somebody want to tell me what iron is? What number it is? Somebody said it. So what atomic number? Number 26. Okay? Remember that we've had numbers 1 and 2 in the Big Bang. And we can make, by sticking things together and releasing energy, we can make up to number 26. But that doesn't account for all the things up to number 92, right? So we still have to make all those. And we haven't even made this yet. We've only talked about making helium. So we'll get into that. For heavier elements, it actually will give you energy by falling apart. And that's actually what things like uranium do. They fall apart and release energy, and that's how we use them for fuel. Okay? All right, so let's go back to, we've got hydrogens, we're making helium. In the process, we also make some other things. So our first step in making from hydrogen into helium, we made this thing that's a hydrogen with an extra neutron, right? Well, that also means that if I've got some neutrons flying around, I can add another one and make a weird thing called tritium. Over here, I've made this helium. If I can add another proton, I can add another hydrogen, I'll get lithium. If I can add another one, I get beryllium, and so on. And so you can start to make all sorts of different things. But in the Big Bang, you don't make everything. You only make those smallest things. So what is it that stops things from forming? What is it that stops you from keeping adding more and more and more?
Heat.
Somebody said something.
Heat.
Not heat. It's not. So actually, heat is what you need. What is it that stops them from coming together? No? So what is the property of a proton? Okay, so if I'm trying to bring my protons together, what's going to happen? So like charges will push apart. Just like if you've got magnets and you try to put the north poles together, they push apart. Same idea. You bring the positive things together, they're going to push apart. And so, and it gets harder and harder the more positive it is. So if you've got two hydrogens, that's a 1 and a 1, you try to push them together. You need a lot of heat actually, because you need them moving fast to get it to do this. But if you've got a 2 plus and a 2 plus, that's now 4 times harder. You have to multiply them. If you have, say, carbon, which will be a 6 plus and a 6 plus, now it's 36 times harder to bring it together. And so that's why it stops. You don't have enough heat. The heat is what gives you the energy to bring it together. And the universe is spreading out so fast that you lose some of that heat. You also get too spread out. And so it stops. Okay? And so electric propulsion is the way that we would term this, or sometimes Coulomb propulsion. And so we've got the light charges are repelling, and that it is because of the positive charge of the nuclei, whether they've got neutrons or not doesn't matter, it's how many protons does it have. And so it gets harder and harder for the bigger and bigger elements. Okay? And so to bring them together, you need to have them moving fast, that's a high temperature, and you need to have them packed in close, that's a high density. And the only place that you can do that after the Big Bang spread out too much is inside stars, which is where we decide we need to do. Okay, so we've got from the Big Bang, we've made some protons and neutrons, we've stuck them together to get some helium, there'll be a little bit of lithium and maybe a little bit of other things, but insignificant amounts. And then they start combining, there's a bunch of electrons around, they pull down, and now it's making just regular elements that have got electrons on them. And then it takes 1 billion years before we get stars. So the universe has to get to being 1 billion years old before we can make any of the heavy elements. Okay? And at that point, you start to have clouds of gas that then collapse and make stars. And I'm not going to get into the details of that. I maybe give a talk next semester on how to make stars. But in the process of making a star, you produce heat and you cause these things to start doing fusion. That's how the sun is making light, that's how it's making energy. So, and we call that fusion nucleosynthesis. All it means is making nuclei. It's making new elements. We call it nuclei because it's just the middle bit that we're making. Okay? And so we have this life cycle of what stars do. And we start from having a cloud of gas that is this one up in this corner. And then it will collapse under its own gravity. And then you'll get something like this. And all of these little knots, I don't have a laser pointer. Where's my enormous scary stick? Wielding the baton. Okay, so these little dots here, each one of those is becoming a star. So this is a big cloud that's then collapsing to make lots and lots of stars. Each one of those will end up something like this, where you've got a star forming, and then it's got the remnants of the cloud around it. That will give you planets, and then a star. But you can only do this if you have some heavy elements. First generation of stars could only have hydrogen and helium in them. You haven't made anything else. And you can't make dust out of hydrogen and helium. Hydrogen isn't solid until you get down to almost absolute zero in temperature. Helium is the same. So you can't do it. Okay? So we made a star, and now we need to do some other stuff. But we need to talk about a few steps that it goes through. And there's this concept that's called hydrostatic equilibrium, which is really not that complicated. But basically, it's whenever you get a balance of pressure and gravity. So I've got my big ball of gas, and gravity is trying to pull all of that mass of the gas down to the middle, right? But it's a gas. It has gas pressure. And the pressure is trying to push it out. And at some point, there's a balance between those two. Gravity's trying to pull in, and pressure's trying to push out. In fact, what it leads to is exactly what we see in our own atmosphere and in our oceans, is that the stuff at the center will be the densest and the hottest, and as you move out, it will get lower pressure, lower density as you move out. And that's what we see in our own atmosphere. As you move up in the atmosphere, it gets lower and lower in pressure and density. Same in the oceans. As you go down in the ocean, it gets higher pressure. And so the same thing in the star. So now we have a star that's really hot and dense in the core, and less dense as you move out. Okay? So now we need to talk about what happens in these stars, because a star like the Sun isn't actually making much more than helium. So we still don't have anything to make life with. And we need to talk about what happens during the different phases. And it's all about this high static equilibrium. And so basically what you have is, what's winning? Is pressure winning, pushing out, or is gravity winning, pulling in? And so before a star becomes, main sequence is basically the term used for a regular star. A star that is just like the Sun, a star that is basically making helium in its core and not doing anything else exciting. Before it gets to that phase, it's collapsing, and gravity is winning. But then it can make helium. What happens when I stick hydrogens together to make helium? I release energy, through E equals mc squared. Energy is released. So now I can heat my gas and it gets more pressure. You heat up the gas, the pressure goes up, right? The thing about this is if you're just driving a car, the tires get hot, the pressure goes up in the tires, right? So you've got, the pressure goes up because you're making energy, heating up the gas, and then it balances. And that gives you the main sequence. That's when it's just an ordinary star and it's mostly just balanced. We'll talk about how it deviates from that in a second. And then, eventually, it's going to run out of fuel. You've only got a certain amount of hydrogen, and only the stuff that's really in the core, where it's really hot and dense, can do fusion. And eventually you're going to run out. There's only a certain amount in there. And so, when that happens, it goes through some entertaining steps of dying and leaving behind some fairly attractive corpses, which hopefully I'll get to show you. Okay, so during the collapse, they're basically just, you could see them, they're shining, but they're just shining because they're hot. They're not shining because they're making energy. They're getting smaller and smaller all the time, okay? And they're getting hotter and hotter until they start fusion, and then you have hydrostatic equilibrium. And that's when you have a regular star. What happens next is really interesting, though. And this is that, basically, in the middle of the Sun right now, it's taking hydrogen to making helium. And we heard it's 600 billion tons, kilograms, of hydrogen is converted to helium every second. But that means that every time you do that, you've gone from having 4 little things bouncing around to just one. Which reduces the pressure. Pressure goes down. What matters for pressure is how fast are the particles moving and how many are there in a certain volume, right? So if you've got a volume and you've gone from having 4 particles to just 1, the pressure goes down. Okay? What happens if the pressure goes down? Gravity is going to win, right? But when gravity wins, it actually causes it to collapse just a little bit, and that causes everything to speed up because it's going under gravity. So I want something harmless I can drop on the floor. What's going to happen if I drop this? How can I make it out of the If I let go, what will happen? It will speed up until it's ground, right? So if gravity wins, all those atoms speed up under gravity, which means that the pressure gets higher. And so very quickly, you're back to hydrostatic equilibrium. Okay? So constantly, the Sun is readjusting itself. It makes a helium, it has to shrink a bit and readjust. It makes a helium, and it has to shrink and readjust. It has some really interesting knock-on effects, though. So the pressure drops, the core gets smaller, but it's only the middle of the Sun that gets smaller, and it gets hotter and denser. So it's denser, it's easier to do the sticking the particles together. And so actually what happens is that the rate at which you stick hydrogens together goes up. And so that means that the Sun is getting brighter. But what matters is, for each one of those reactions that you do, each time you have 4 hydrogens makes a helium, you give up a certain packet of energy. If you do that more often, then more energy comes out every second. And so the Sun is going to get brighter. And so for the Sun, over its approximately 5 billion year lifetime, it has gone from being about 10,000 Fahrenheit to about 10,500. It's not a huge change. It's changed in radius, it's changed in brightness, and it's changed in temperature. Okay? And in fact, it is getting hotter and larger and brighter every day. Don't let anybody tell you that this is causing global warming. Bear in mind that it has changed by 500 degrees over 5 billion years. You cannot explain recent changes in climate. But it is something that will affect our climate on the timescale of billions of years. So in a couple of billion years, it will be hot enough and bright enough that it will be a problem. I don't expect us to be around at that point. Okay, so most of the time, this is all we're doing. So we still don't have any heavy elements, right? We've only got hydrogen and helium. We've got to make some more interesting things, especially carbon and oxygen. So we need to look at what happens when the star starts to die. And so basically, like I said, this is when it runs out of hydrogen, you make helium, and you can't stick them together. Why can't you stick the heliums together? It's hot enough to stick hydrogens together, but it's not hot enough to stick the heliums together. Remember, they're 2+ and 2+, so it's harder to stick them together. For different types of stars, you'll get different things happening, and we'll go through both of them. If it is a high-mass star, it will explode in a supernova and leave behind something that looks like that. That's a Veil Nebula. This is actually showing you a supernova that went off next to a galaxy. This is how bright it is compared to a whole galaxy. Basically, it's the brightness of a whole galaxy, very, very briefly. This is probably the most famous remnant of a supernova. This one was witnessed about 1,000 years ago in China, and so there are records of this one exploding. And so it's something that we have really good records on what it's doing, and it's also close enough we can do interesting stuff. But it's not just these big stars. The sun won't do this. The sun is not going to explode. It's still going to kill it, but it's not going to explode. But it still throws off material. It still makes new stuff. It still throws it out, and it still leaves behind an attractive cause. And so this is a planetary nebula. This one doesn't have a name. This is the Helix Nebula, which I've done some work on, and is one of the closest to the Sun. And this is one that hasn't got very far along yet, called the Egg Nebula. Okay, so what's happening during this phase? We have to think about how are we getting those heavy elements made. Well, we've run out of hydrogen. We've got a core made of helium. It can't stick things together, so it's not got an energy source. So it cools down, right? The heat just keeps flowing out of it. It cools down, so the pressure goes down, so gravity wins, and it shrinks. And as it shrinks, it's speeding things up, so it heats back up again. And what you do is then you drag along an outer layer. So when you have this star, you've got this enormous star with a tiny little core. This thing is collapsing, and then the material around it will also collapse, right? And that's still hydrogen. So you can heat that up by causing it to collapse down too, because it's being accelerated and going faster. And so that's where you can start having fusion. So now you're still making helium. I haven't made anything else yet. But it's not in the core of the star, it's around the core. Okay? This is important because it allows us to understand what happens in successive generations. So now I've got this thing here. It's making energy, and the energy is going in all directions. So it's going into the core, but it's also going outwards. And I've just got this big ball of gas. And as I heat it, it's going to expand. Because that's what happens when you heat gas. It's not confined. It's not confined on the outside. And so it will expand, and that causes the surface to cool. And this becomes a red giant. Okay? For a star like the Sun, when it does this, its surface will end up somewhere, it won't actually get as far as ours, probably between Mercury and Venus. So it goes down to about 3,000 kelvin, about half its current temperature, but its surface is much closer to us. And at that point, the surface of the Earth will not sustain life. Okay? It will be really, really hot. This will happen in about maybe 6 or 7 billion years. So it's not something you have to worry about imminently. But we've been collapsing down the core, and it's getting hotter and hotter, and eventually it's going to get hot enough that you can stick the heliums together. And that doesn't happen until you get to about 100 million Kelvin, but now you can stick heliums together. Okay? And so what's happening here is, actually it turns out that if you just stick 2 heliums together, it makes something that's unstable and just falls apart. So you actually have to stick 2 together and then add another one really fast. And then you get carbon, because now I'm going from having number 2 to number 6. I'm going from He to C, and I make carbon. And so this is the thing that's going to happen inside my stomach. Right? Once I've made the carbon, then I can add more. So if I've got helium, I've got lots of helium. If I can add helium on, the next thing I make is going to be oxygen. If I add another helium on, I get neon. If I add another helium on, I get magnesium, and so on. And I can keep doing this. I keep adding more heliums, and I get up to iron and nickel. Okay. Actually, a star like the Sun won't do this very effectively. Why? We still have too much propulsion. Remember that it goes as the multiple of the two pieces. So if I've got carbon, which is 6, and I want to add a helium, now it's 12 times what it was for hydrogen, right? But if I want to add that to an oxygen, now it's 16 times, and so on. And so it gets harder and harder the bigger the elements are. And so you get a little bit of this happening, but mostly it's just making carbon shift time. But as we go on through the elements, you'll see we can make all of these different things. Okay? You can also then add on other things, because you've also got hydrogen floating around here. And so you can add in some hydrogen into those pieces. So if you've got a carbon and you add a hydrogen, you get nitrogen. You add another one, you get oxygen, and so on. So you can start to make everything. Okay, so what happens next is eventually you run out of helium in the core. And we go through another phase exactly like we did before. So we went from having hydrogen in the core to helium that wasn't burning. And then we went from helium in the core to carbon that wasn't burning. Okay? So that's what we're saying here. We've got, the first time around, we've got a core that's made of helium and a shell around it that's got hydrogen sticking together. And then loads of gas that's not doing anything except expanding. Now, we've had helium sticking together. Eventually you're going to run out. And you'll run out way faster than you did with the hydrogen. Because you've got a quarter of the number of particles and you're using 3 of them at a time. Okay? And so now, but you'll end up with the same thing. You've got this carbon. It's going to shrink down. And then that'll drag around some of the helium that was made that will then switch on. And that will drag down some hydrogen that is not been used yet. And so you get these shells. Okay? And this is going to happen successively. Now, if you've got a low mass star, this is where you get stuck. And you get stuck because there's this interesting property of matter that says you can't just arbitrarily stick it closer and closer together. There's this thing called the power diffusion principle that says if you have electrons, you can't keep putting them closer and closer together. You can't. They can only exist in different states. Okay? So the problem is that along with all these carbons, to each carbon you've got 6 electrons. And they're in that core as well. They're not taking part in the nuclear fusion, but they're there. And so as this thing shrinks down, eventually it gets so small that the electrons can't actually get any closer together. And that stops it from shrinking. Okay? And so it just sits there. It's not doing anything. And I don't know how many of you have seen like news articles about diamond stars and things like that. This is how it gets made. It's what's left. Okay? It's a carbon thing that's got as small as it can, and the electrons won't let it get any smaller. Okay? But it still has some hydrogen burning and some helium burning going on, and at the same time, this is the star. So this is my low mass star, and let me show you what it's going to do. You've got fusion going on in the yellow part, and it's doing this, and it's also churning material up from down below. So the stuff that gets made down there gets pulled up to the surface. Okay, so we've got to the surface of the star. How do we get it off? Well, I said that when it's a red giant, it has its surface somewhere between Mercury and Venus, right? But if it goes for a second red giant phase, now it's got carbon in the core, and it's got helium around that, and hydrogen around that. And now the surface is out by Mars. We've been involved. The surface is out by Mars, but let me show you the pulsation again. It's unstable, and so it's doing this. Now, we're talking about something that's the same mass as the Sun. It hasn't got any more mass than it had before, and its surface is a long way from where it was before. It's way, way out, and it's doing this. So the surface gravity is really low. And it's doing that. So every time it does that, material can escape. And as that material escapes off into space, some of it came from deep inside, so we can get out those elements that were made deep inside. Okay? Okay. And so we get that material ejected. So that's really important. Now, I'm going to leave that there for a second, because we've made carbon, and we've made helium, but we haven't made anything else yet. Actually, these stars make a whole bunch of other things, but we haven't quite got to that yet. And I want to talk about higher mass stars. Before I do that, I just want to show you the courses of these things. So all of this is the material that was thrown off by the star. Okay? So it does this for about 1 million years, and it makes this big nebula of gas that has been thrown off, and this is what's left afterwards. And so this is the material that was thrown off the star. They're called planetary nebulae. They have nothing to do with planets, but this is the first one that was discovered more than 2 centuries ago. Most of these are Hubble Space Telescope images. Okay. But all of that material is drifting off into space. It was once part of the star and contains the new elements that have been made. And that's going to drift off and join stuff from other stars, and so it's part of our life cycle. So for the stars like this, they do this for about, let's say, it depends on the mass of the star, but it's somewhere around 100,000 to 1 million years. And they just start off gently. So it's not a really dramatic event. It's not like a supernova. They make lots and lots of carbon. They're very good at making carbon. In fact, most of the carbon in you came from these sorts of stars. They're much more effective at making carbon than high-mass stars. And so, not only do they make more carbon, but it's easier to make low-mass stars than it is to make high-mass stars. So although a high-mass star can make other things, the low-mass stars dominate when it comes to carbon because there are just so many of them. So most of the material that is carbon in you will have come from these sorts of stars. Okay? Some oxygen too. Oxygen is a little trickier. Okay, so let's talk about what happens when you have a high-mass star. Well, when you have a high-mass star, you keep going through those successive red giant phases. So basically, you had a hydrogen core, then you had a helium core, then you had a carbon core. But because it's really hot, it's much, much more massive, so it gets hotter when it forms. And because it's hotter, the electron thing doesn't kick in until later. And so it can stick the carbons together. And then it can stick the oxygens together. And then it can stick the magnesiums together. So you just keep going through these successive cycles until eventually you have this onion, where the center is made of iron, and then you have silicon, magnesium, and neon, and all the things that you can make by sticking hydrogens together, basically, heliums together. And I have another version of this that is just a little more simplified, so you can see you've got iron in the core, you've got silicon making iron around that, you've got oxygen making silicon around that, carbon making oxygen around that. This is simplified. It gets really complicated when you look at it in detail. You can also see how long each step takes. So for a star like this, which is about 25 times the mass of the sun, it's going to use up even its main lifetime, its main sequence lifetime, that's turning hydrogen to helium. It's only 7 million years, which is real short compared to the sun's. But then the next one is only 700,000. It's only going to last 600 years on carbon. And once it gets to doing silicon, it's only got a day left. Unfortunately, we can't see inside them, so we can't predict when that's going to happen. But Betelgeuse, for instance, is doing this. And eventually we will get a very impressive supernova because it's close enough to it to be pretty bright. Probably about as bright as the moon. Okay, so once we have iron in the core, that's when things go weird. And like I said, you can make iron by fusion. But after that, well, you can do fusion, but it uses energy. So if you've got up to iron, as you stick things together, you release energy. And so you're giving stuff back that helps the star to stabilize itself. But now, if you try to stick anything onto an iron, you have to also give it some energy. And so so anything that you do will use up more. So the temperature is not only going down because you have no energy source, but you're using even more, so the temperature goes down faster. Okay? And you're also at a point where the temperature for sticking things to iron is very close to the temperature for making it fall apart into its pieces. So actually what happens is it gets hot enough that instead of sticking things to the iron, you actually make it fall apart. And so you no longer have any iron left. These sort of supernovae do not make iron. Don't let anyone tell you that they do. There's lots of textbooks, there's lots of TV shows that say, this is where you get iron from. It's not true. The iron in the core is completely destroyed. It's taken apart, it falls apart into heliums, and then into hydrogens and neutrons, just falls apart into its constituent pieces. But it's still collapsing. It has no source of energy. It's collapsing so much that the protons and the electrons stick together. And then all you've got is neutrons. Okay? So now you have this big ball of neutrons, and it's going down and down and down, and there's nothing to stop it. Except that neutrons obey the same laws as electrons, only they can get closer together. And so now they come to a stop, because you can't stick them any closer together. They have a rule about how close together you can put them. And so now, they're stopped by, we call this degeneracy. They're stopped by the fact that you can't get them to go any closer together. So now consider, I've got this thing and it's collapsing, and I've got this thing in the middle that's now completely solid, and it can't move. What happens is all the bits of gas fall down onto this solid sphere in the middle. What would happen if I got something in here? Let's see. Something that won't break apart into a million pieces. What's going to happen if I got this? What did it do? It bounced. So now you've got all these atoms and they're going to hit something solid. What's going to happen? The amount of bounce energy then propagates all the way through what's outside of it. So all of those nice, neat onion shells of stuff get thrown out. And that is your supernova. So that's how you get out all of those nice things. So those sort of supernovae are very good at making those helium-rich things. So you've got lots of silicon, lots of oxygen, magnesium. But there's a whole bunch of elements in between that won't make that way. Right? You can still make some of those. But basically, we've now made elements of 270 silicon. You can argue about iron. You can ask me at the end about this. So back to, here we have a supernova. It's exploded. And here we've got, so this is the Crab Nebula again, one we already saw. The one on the other side, this is probably the most famous supernova to happen in my lifetime. You could see it from the southern hemisphere. It's in the Large Magellanic Cloud. Happened in 1987. It was supernova 1987A. And it was probably the most famous supernova, certainly in a few decades. But like I said, we've got things up to iron, but we haven't made anything else. So how are we going to make it? Well, we do it by something called neutron capture. So remember that an atom is made up of protons, neutrons, and electrons. We don't need to worry about the electrons. They're not important for what the element is. What's important is the protons. But neutrons are neutral. They don't have any charge. So adding them in is much, much easier than trying to stick together these positive pieces. And so you can stick them together. There are certain reactions that are going to happen that will make neutrons be ejected from other neutrons. So you've got spare ones floating around. So here you can see if I've got this carbon-13, which you can make carbon-13 if you add a hydrogen to carbon-12, and it will decay and make carbon-13. Just like when we stuck two hydrogens together, one of them turns into a neutron, do it the same way. So now we've got carbon-13, so it's carbon, but it's got an extra neutron. You add a helium, it's going to eject another neutron. Likewise with the other reactions. Depending on what is stable, what is the most energy efficient way for that atom to exist. And so you get these neutrons thrown in. So now you've got these neutrons, and they can add in. And so what matters now is how fast can you add them in. Okay? If you add them in rapidly, so let's say I've got an iron. I've got an iron with 26 protons and 30 neutrons, and I add in another neutron. It's still iron. And I add in another neutron. It's still iron. And I keep adding in neutrons. It's going to make a version of iron that's really, really unstable and radioactive. Okay? But then it will decay radioactively and make a new element. That's all that happens in these things. If you have something that has too many neutrons, it will do what's called beta decay, which turns the neutrons into protons. So now I've got my iron, and one of its neutrons gets converted by beta decay, and it makes the next element. It's added a proton, and then the next one, and then the next one. But depending on how fast you add them. So as an example, for iron 56 is stable. That's the thing that we're going to start from. If we add in a neutron, it's still stable. It's not going to do anything. If you add in another neutron, it's still stable. If you add another one, it's not. So it'll decay and make something else. However, you might be able to add a neutron before it decays. And then you'll make a different thing, because the radioactivity is different. So depending on how fast you add your neutrons, you will make different elements. If you add them very fast, we call it rapid neutron addition. And if we add it very slowly, we call it slow neutron addition, because we're really inventive with names and so on. Okay, so for the rapid process, The rule is that basically you keep adding things so fast that it doesn't have time to decay at all until it gets to something with such a short lifetime that it's not going to exist. And that means that you have to have lots and lots of neutrons. And this is going to happen in the high mass stars because that's where you have more reactions that produce more neutrons, so you have a high density of neutrons. Let me just back up for a second to show this. If you look at this, the only one of those reactions that's going to happen in a low mass star is the first one. The others you're only going to get in higher mass stars. So those higher mass stars are going to have more neutrons floating around. So they are going to have this much higher density that lets you add them in really, really fast. Right? On the other hand, if you've got the slow process, now you add one in and you wait to see if it's stable or not. So if I start from, say, carbon, I've got carbon 12, I add a neutron. It's still stable, carbon 15 is stable. I add another neutron, it's carbon 14, which is famously unstable. But it's got quite a long lifetime. But basically the rule is you have to wait until that turns into the next thing, which is actually nitrogen. And now you can add another neutron. And so you get a completely different pathway of things that you're going to do. Okay? And so for this you actually have to have really long times, so you need to have low densities. So this only happens in those lowest mass stars. But even a low mass star like the Sun, when it dies, can make all of these elements up to lead. How much of each one it makes depends on exactly what pathways are taken. And in fact, most barium and zirconium come from these low mass stars. They're made preferentially in low mass stars. And it's to do with the pathways, which if anybody's interested, I can get into detail later. And so this is how we can make everything. So you basically make really silly elements, and then you end up with something that is the elements we're used to, but which ones you get depend on how fast this reaction. Okay? And so now we've gone from having energy to particles, to protons, to atoms, to stars, and now we can start making planets and life. Okay? So all of those atoms that were made inside of these stars get thrown out. If it's a supernova, it's thrown out explosively. If it's a low mass star, it's not explosive. So here is kind of the schematic of that. So we've got the star here. It may have life forming around it, but let's not get there yet. When it dies, it becomes a red giant. If it's a low mass star, it becomes planetary nebula. But either way, it's throwing off material into space. If it's a high mass star, it's going to go supernova. But it's still throwing off material into space. All that material contains all those new elements that have been made, and now it can make new stars and new planets, and now it's got the stuff that's inside of us. So, this is basically the path that we've taken from the Big Bang through making stars, through producing elements and dispersing them, to making planets like the Earth, and it all comes from making stardust from these things. Thank you.
Dark matter and dark energy. What you talk about is 7-8%. Do you know anything?
No, we know nothing. So, for dark energy, we know less than we do for dark matter, but either way, we know that there's something that's, for dark matter, we know that there's something that is behaving like mass, and that we can see its effect, but we can't see it, so we have no way of probing it. For the energy, it gets even weirder, and it won the Nobel Prize, was it last year or the year before? We know that we have this empirical observation that says the universe isn't just expanding, the expansion is getting faster. And the way that you should think about this is, if you think about the Big Bang as being, you've got a certain amount of energy contained in this thing, and when it explodes out, at some point, if it's got exactly the right amount of energy, it'll keep expanding forever until that's just forever. If it's not got quite the right amount of energy, it keeps going, but there's all this material in it that's trying to push it back, so it should slow down, until eventually it'll come back down. And I think that it's being like a bouncing ball. You give it a certain amount of energy, but eventually gravity's going to pull it back down. You've got a certain amount of energy, but eventually gravity's going to pull it back down. The term dark energy is just saying, there's some energy that's making it speed up. We don't know what it is. And that's all that the term really means. So we have empirical evidence that suggests that it's going faster. Even that, I would argue that there are some things that have been overlooked in our analysis, but that's as much as we know. Any other questions? Okay. Is it clear of that? 50-50? Okay. Well, you may get to see things on the roof and you may not. But if not, you'll just have to come next week instead. And we'll have another one of these in a month.
We're not under those two since you still can be continued.